So this is the metapopulation lecture for this unit. And how I wanted to start out thinking about metapopulations is not talking about metapopulations, but when we think about the way that ecology is kind of like taught, and in these equilibrium-based models, and these really, well, I shouldn't say equilibrium-based models, but real simple models, is that a habitat and a population grows without immigration and emigration, right? Like it's like a closed system. And that system itself is completely homogeneous from the environmental perspective. Like one spot in the system is exactly the same as another spot. And I mean, even with this logistic growth model here, there's no mention of the environment actually itself. So from the environment, the species themselves are the same in each part of it, and the species then are free mixing, meaning they can basically go wherever they want. And so the species are always there, and whether we're talking about the logistic growth model over here or the Tillman's R-star model, two of the main models of competition, and then this is looking at population growth. These models are not spatially explicit. Okay, so this lecture is going to look at some of those things and see how, when we start to add like things about space, we get some really interesting interactions that can then really influence conservation. So let's go back to thinking about this habitat selection model. Why do we find a species in a given area, right? Now, we know that there is some truth to this. These things all make logical sense, right? So for a species to be in, for this blue butterfly here to be in this habitat, it needs to have gotten there. It needs to have like conditions that are actually conducive to its survival, and it needs to have the lack of predators and the availability of its food source to actually then survive in the habitat. Now that makes sense, right? But there's still no like spatial ideas in this theory. So all this idea here all assumes that organisms are extremely free mixing, meaning they can get there basically if they want to. Everything pretty much gets everywhere, and is the organism's niche then determines whether it's present or absent, right? So it's this last step here is looking at that realized niche. Okay, does the realized niche of the organism exist such that it could survive there if it has gotten there? The question then that this idea of metapopulations gets into is, what if migration is not a global consistent thing, right? So species might not get there just due to complete randomness. So this brings us to the idea of metapopulations. What is a metapopulation? It means a population of populations. Another way to explain it is subpopulations in a larger landscape, or local smaller populations that are connected via migration. Now, let's say that there's a species of mosquito in this lake. Well, it's probably in this lake, probably in this lake, probably in these tiny little, all these different ponds. But in some ways, the single mosquito that's over here is, it's connected potentially to this one. Potentially, when this one mates, it could mate with an individual from over here. But the farther away you get, the more rare that interacting, those species would interact. And so if we think about, there's lakes here that have some of these species. Let's say the ones where I cross have them. And then there's some lakes, for whatever reason, might not have the mosquito species that we're looking at. So this idea comes from this guy named Levins, and his metapopulation model is really, it's still pretty simple, right? But there's some really interesting dynamics that are super important for conservation that we'll see here in the next lecture. So this simplified spatial model uses different patches, okay? And I think the easiest way to think of this is, if this is just, Lake A, this is Lake B. Now, these could be forests, these could be prairie patches. For now, let's just think about it as lakes, just because, that the border of a lake makes a little bit more sense, okay? And let's ignore that there's rivers going between lakes and all that kind of thing. So this is why it's still a pretty simple model. Now these lakes then are connected via migration. Okay, let's say there's a species that's not a fish that has to swim or something, but they could be ducks or I don't know. Maybe mosquitoes are a better example because they have, some ability to fly and migrate, but not that much. They can't fly, like hundreds and hundreds of miles. So these different lakes then with these mosquitoes in them are either occupied or not, right? So here the blue is occupied. Should have written smaller, right? So, but we don't think about population size in here, right? So this is Lake A here is occupied, and it might have, 10 mosquitoes per meter squared. That's actually a pretty low number, but if this lake here has 5 per meter squared, we're not thinking about that. That doesn't matter. It's just whether it has it or not. So this is occupied. And so when we think about the abundance in the entire region, right? So we're really thinking about the regional abundance. What we're saying here is just the number of patches occupied here. So this in this case would equal 3 here. So we would say that the abundance of this species is 3 out of this 6 different patches here. So each patch, though, has some level of extinction. We'll call that M here. There's also colonization. So when we think about, these mosquitoes going from lakes to lake, over here, there's some per patch colonization rate that this lake here, what did we call it? Lake B, right? Lake B has some chance of, of being colonized with that mosquito. So another thing about this is that the fraction of currently occupied patches is P here. So that in this case this equals 3, 3 out of 6 here. And unoccupied patches is just 1 minus P, right? So in this case it's just, again, 3 out of 6, right? So determining whether a patch gets colonized is a little tricky. I guess I shouldn't have said it's just C up here. I forgot about this, that it's dependent on the current population size, right? So remember that population size, let's go back here, is just the abundance here, the number of patches occupied. This is what we're looking at, right? Now, so the colonization, is more likely to happen if there's a couple things, right? So this per patch colonization rate is just constant. But, basically as the population size, that is P, as that population size gets bigger, the more likely that patch is to get colonized, okay? And so basically the more, the bigger the population size is, the bigger the more likely that that species is going to be able to colonize a given empty patch. And what this kind of leads to is this little patchwork of, places getting the species and it going extinct. And the species are just kind of hopping around all over, and that depends on that extinction rate and that colonization rate. So what we see is, at any given one time, it's not necessarily the same patches that have the species, and they can go all over the place. And this is why we call it like metapopulations, populations within a grander, bigger scale. Now, what we see then is population growth. This is the logistic model, right? And this is the metapopulation model here. And what we see is they're highly analogous, right? And this is the equation for that metapopulation growth rate. And what we can see is we're all familiar with this equation. The R here is that per capita growth rate, right? Well, that's here. This is essentially that R. That's the same thing here, where this colonization minus the extinction is like basically that the rate of growth. It's just like the little R here. And this P is our population size, exactly the same as here. And then what we can see is the 1 minus M over C is actually the carrying capacity. And what there you're never going to have like full the patches are never going to be 100% occupied, and that's due to this thing here. We'll talk about that in a little bit and the consequences of that. But this P over 1 minus MC is exactly the same thing as looking at this N over K. So you always have these unoccupied patches. Now the fraction of those unoccupied patches is this thing we call P hat, and it's 1 minus M over C. Okay, basically because you have a continuous extinction rate, background extinction rate of a species in a given area, that means that your patches are not always going to be occupied. Okay, so if you think about it, the M is that extinction rate. The higher the M is, what you're going to get is the P hat is going to be, there's going to be more unoccupied patches, essentially. And what happens then is, okay, so we know that always you'll have at least some amount of empty patches. When you then start getting rid of patches, and through habitat destruction, that decreases population growth over time. Like basically, the fewer patches you have, there's less total area. So in that sense, you'll have less total area. So yes, of course, population is going to go down, but there's this extinction threshold. So when this decreasing patch number, which is D here, equals 1 minus M over C, that's the fraction of unoccupied patches, essentially then you have an empty metapopulation, and you get extirpation in all of those patches. So maybe let me kind of like go through that one more time, right? We know based on the M and C, the extinction rate and the colonization rate, you're always going to have unoccupied patches. You'll never have a model where it's completely full, okay, where these are all blue. As you then start to get rid of patches, you have less total area and population will go down. Once this decreasing patch number equals that proportion of unoccupied patches, then you get essentially, basically in this case, a metapopulation that is completely empty of your species of interest. So what does this model is not perfect, right? We know that patches vary, right? The assumptions of this model was that each individual patch is the same. Okay, well, look at these islands over here, right? This island is certainly not the same as this island. There are differences in elevation, differences in size, differences of whether it's protected from, waves or not. So things like population growth rate are going to be different. Resource abundances are going to be different. The ability for a species actually to migrate to it is going to be different, right? If we put another island way over here that's super far away, is a species going to be able to swim that? And that's a big question mark. It'll depend on the species, and we just don't know. So an extinction on these islands are not equivalent due to being different sizes and all these different things. There's patches are going to vary. We know that. But this model chooses to ignore those things, and it still brings up, but that's not necessarily a problem. While it does ignore these things, it still brings about really interesting conclusions that we'll talk about here coming up. This is also an equilibrium-based model, right? And I know that there's we've talked about this a variety of times in class, that equilibrium versus non-equilibrium, when we know that conditions vary. So equilibrium models are kind of like by definition wrong, but it still shows us a lot about the system. So, and how we should be making conservation decisions, or how we should be understanding these systems in their fundamental sense. So it's not necessarily a problem. All right, with that, we'll come back and talk about how this metapopulation model determines or informs conservation decisions. With that, see you later.